I'm Zilhalawani. I will present about the literature review and the multiple reaction for the production of aniline. The first process to produce aniline is hydrogenation of nitrobenzene in fluidized bed reactor FBR. We can see that 0.1 mole fraction of nitrobenzene and 0.9 mole fraction hydrogen fit in the reactor, where the outlet stream is 0.995 mole fraction aniline and 0.005 mole fraction of water. The conditions that apply in this process are 270 degrees Celsius and 1.5 atm. The reactor conversion and selectivity for the manufacture of aniline are 99.7% and 99% respectively. The second process is ammonolysis of phenol in packed bed reactor, PBR. The temperature and pressure that required for the process is 367.9 degrees Celsius and 16.38 atm, where the reactor conversion and selectivity are 95% and 99% respectively. Next, let's move on to the background of the aniline. What is aniline? Aniline is an organic compound with the formula C6H5NH2 and have molecular weight 93.13 gram per mole. This aniline is consisting of a phenyl group that attached to an amino group. Moreover, it has the odor of rotten fish. Aniline is mainly used as feedstock for the polyurethane industry. Besides that, aniline is corrosive, acute toxic, health hazard, irritant, and environmental hazard. Then, we take a look at the physical properties. This table summarizes the physical properties of aniline.
Synthesis route. For this project, we will compare between two types of synthesis aniline. First, hydrogenation of nitrobenzene to produce aniline. The second reaction forms a byproduct, cyclohexylamine. The conversion of nitrobenzene in the reactor is 99.7% and selectivity to aniline is 99%. Type of reactor is fluidized bed reactor because catalyst is used to catalyze the one-step hydrogenation. Second, ammonolysis of phenol by forming aniline directly from carbonyl compounds using hydrogen mixture. Second reaction forms a byproduct, diphenylamine. Third reaction is decomposition of ammonia. The conversion of phenol in reactor is 95% and selectivity to aniline is 99%. Fluidized bed reactor commonly used by placing phenol over a silica alumina catalyst in the presence of excess ammonia. There are several types of reactors. The most typical reactor to produce aniline is fluidized bed reactor. Aniline commercially been prepared by using catalyst. For most reactions, this reactor gives the highest conversion per weight of catalyst of any catalytic reactor. This reactor can complete mixing to produce uniform product. It also widely used in manufacturing field. All things considered, hydrogenation of nitrobenzene is the best process to produce aniline. By comparing, hydrogenation of benzene is more effective compared to ammonolysis of phenol. Moreover, this process gives highly profit compared to ammonolysis phenol.
For the process of hydrogenation of nitrobenzene for the production of aniline, the main reaction is nitrobenzene plus 3H2 with the act of catalyst yield aniline plus 2H2O, where the rate of reaction can be deduced as rate of disappearance of nitrobenzene equal to K rate constant multiplied by the concentration of nitrobenzene and multiplied by the concentration of hydrogen at power of 3. So the value of K can be determined from the Arrhenius equation as shown on the screen, where the value of activation energy, frequency factor, and rate constant can be determined experimentally. Therefore, by taking ln at both sides and compare it with the linear equation, the value of EA, A, and K can be obtained from the graph. By referring to some journals, the value of EA and A for the process of hydrogenation of nitrobenzene to aniline are as shown in the table. At temperature of 270 degrees Celsius and at fourth order of reaction, the K can be calculated by using EA and A at gas phase, since the reaction react at high temperature. So the K is 0.01058 gram at power of 3 per mole at power of 3 minutes. By applying the equation of reaction rate, the rate of aniline production is 15.5 10 power of negative 3 mole per gram minute.
Now, let's move to the reactor system. For this reaction, the reactor system is shown as in a slide. From the literature review, we noted that the phase of the reactor is gas, reactor process is continuous flow, type of reactor is fluidized bed reactor, the reactor operates at a temperature of 270 degrees C and pressure at 1.5 atm.
Stoichiometry table. From the reaction and the information given, we can calculate the stoichiometry coefficient. Therefore, we can construct stoichiometry table of reaction hydrogenation of nitrobenzene to produce aniline.
We proceed to the multiple reaction. For the multiple reaction, assuming that all the reactions are elementary, we write the red law for all component species in the reaction. There are two reactions that take place in the production of aniline. One reaction is desired product, which is aniline, and the other one is the production of cyclohexamine, the undesired product. To make it easier for us to understand, we rewrite the chemical equation using the alphabet A, B, C, D, and E. We relate the rates of formation of the other species in reaction 1 and reaction 2 to the rate loss, hence we get the relative rates. After that, we substitute the rate loss for each species in reaction to obtain the net rate of reaction for that species.
For the project calculation, we are required to calculate the weight of catalyst to produce 10 metric tons per annum of aniline, selectivity of the aniline, and lastly, yield of the product. Firstly, calculate the weight of catalyst needed to produce 10 metric tons per annum of aniline. From previous knowledge, the main reactions is 1 mole of nitrobenzene react with 3 mole of hydrogen gas from 1 mole of aniline and 2 mole of water. To make the calculation more easier, the reaction is represented as A plus 3B from 3 plus 2D. From the literature review, we found that the mole fractions of nitrobenzene and hydrogen into the reactor are 0.1 and 0.9 respectively, while the mole fractions of anilines and water out of the reactor is 0.995 and 0.005 respectively. We are also given the value of conversion for this reaction, which is 0.997, and the rate constant is 0.01058 per min. By taking 10 metric tons per annum to calculate the mole flow rates of the aniline, hence we got the mole flow rates of aniline as 0.2043 mole per minute. Next, the mole balance on the fluidized bed is calculated as same as packed bed reactor, which is Fa0 dx over dW equals to negative Ra. After that, we need to know the red law equation for this reaction. Therefore, from the reactions, the red law is negative Ra equals to KCa. As we can see, we are not follow the elementary reaction because hydrogen is present in such excess. The concentration of hydrogen at any time t is virtually the same as initial concentration, and the red law is independent of the concentrations of hydrogen. From the stoichiometric table, sigma is calculated as -1 and the epsilon is equals to -0.1. Then, calculate the Ca0 or initial concentrations of nitrobenzene. Using the equation, Ca0 equals to Ya0 multiplied by Po over RTO. Plug in all the calculated data previously into the equations and we got Ca0 equals to 3.365 times 10 power of -3 mole per dm cube. Hence, the Ca is equals to 3.365 times 10 power of -3 multiplied by 1 minus x over 1 minus 0.1 x times T0 per T times P over P0. To further the calculations, combine the red law and mole balance, we have dx over dw equals to kCa over Fa0. For case 1, which is isothermal and isobaric, firstly we calculate the Fa0 or initial flow rate of nitrobenzene using mole balance. From it, we got the Fa0 equals to 0.02043 mole per min. From combined mole balance and red law equation, plug in all the data and information from previous calculation, we got dx over dw equals to 0.01058 per min over 0.02043 mole per min times 3.365 times 10 power of negative 3 mol per dm cubed times 1 minus x over 1 minus 0.1 x. The equation is rearranged and integrate both sides to calculate the weight. Using calculator, the weight we got for isothermal and isobaric case is 3056.74 kg. For case 2, isothermal and non-isobaric, from the literature review, by taking pressure reactor as pressure feed and pressure out was taken from the literature, which is 1.4 bar. Hence, P naught equals to 1.5 atm while P is equal to 1.38 atm. Then evaluate the weight of catalyst from combined mole balance and Red law equation. Plug in all the data and information from previous calculation. Y is P over P naught or pressure factor is equals to 0.92. We calculate Y since this equation is non-isobaric case. We arrange the equations and integrate both sides to calculate the weight. Using calculator, the weight we got for isothermal and non-isobaric case is 3,323.71 kg. We are required to calculate the selectivity of the main product aniline. From reaction root part, we got desired reaction is nitrobenzene react with hydrogen gas from anilines and water, while undesired reactions is nitrobenzene react with hydrogen gas from cyclohexylamines and water. From the literature review, we found red law desired is 15.5 times 10 power of negative 3 mol per G mean, while for undesired is 15.66 times 10 power of negative 3 mol per G dot means. Then substitute the R desired and R undesired into selectivity equations, and we got its selectivity is 0.99. Lastly, we are required to calculate yield of the product. From the literature review, we found that the reaction rate for desired is same as reactions of nitrobenzene, which is 15.5 times 10 to the power negative 3 mol per G dot means. Hence, the yield for this reaction is 1. In the slide show that the coding in the polymers in order to form a graph. Here is the graph represent the weight of catalyst needed to produce 10 metric ton per annum of aniline for case 1 and case 2.
In conclusion, the process of hydrogenation of nitrobenzene is the best alternative for the production of 10 MTA aniline as it gives high conversion of nitrobenzene, use inexpensive raw materials, produce large product and give high profit. The reactor used is fluidized bed reactor as it gives complete mixing for the uniform production of product. The catalyst used is copper silica catalyst and they are different in weight of catalyst under different conditions, which is isothermal and isobaric and non-isobaric. So these values prove the relationship between the pressure drop and the weight of catalyst. So by increase the pressure drop, the weight of catalyst will increase as well. Besides that, the selectivity of the process is indeed 99% of aniline produced and the yield is 100% production.